Okay, Assalamu alaikum everyone. Thank you for attending today's seminar. Today, inshallah, we'll have Dr. Akramul Azim, who is an associate professor in software engineering at Ontario Tech University. Today, he will give us a seminar titled Performance and Security Constraints and Cyber Physical Systems and Internet of Things. Dr. Akramul Azim is currently visiting the computer engineering department at KFUPM. So without further ado, I would like to leave the floor to Dr. Akramul Azim to start his seminar. Just one maybe note, maybe for the attendees, if you would like to ask Dr. Akramul, maybe you can write your questions in the Q&A box, and I will try to convey the questions to Dr. Akramul, or maybe try to give you the floor to ask you, Dr. Akramul Azim, personally. So the floor is yours, Dr. Akramul.
Thanks, Doctor, for your introduction. Hi, everyone. So today I'm going to talk about two important things in cyber physical systems and Internet of Things. And at any point in time, you can stop me and ask you questions instead of waiting at the end. If you wish to do so, I'm fine with it. Or you can write your questions in the chat box and we can read it after. So first, I would like to go by this question, that what are the differences among embedded systems, cyber physical systems, and Internet of Things? Because the terminologies are quite used extensively in different places. And sometimes we have to be a bit careful when we use these terminologies, because they might mean something different if you are not using them properly. So the way I'm gonna first to define first with the definition of this system. So embedded systems are the systems that you can use for any computation and that has some sort of embeddedness. And obviously, the main point of an embedded system is to do a very specific thing. It's not a general purpose system, so you really do not make an embedded system to do something very general. You want to build an embedded system to do something specific. So that's really a key characteristic of an embedded system. On the other hand, cyber physical systems are embedded systems as well, but it does have some sort of control and sophisticated control in there, as well as some cyber part, which indicates that it does have some sort of communication. The communication doesn't need to be internet, but it does have to be reliable. So there are different sort of communication mechanisms that you can build in to build a cyber physical system. So you can say that the embedded systems, when they have control and cyber, then they become cyber physical systems. Then now we hear a lot about Internet of Things. So Internet of Things is definitely bigger version of all these stuff that we just talked about, cyber physical systems and embedded systems. But in the case of IoT, the goal here is to obviously have a massive sort of connectivity using cloud computing and edge computing and some other sort of computing technologies. And sometimes you connect them using some sort of internet as well, because it does have internet connectivity. And that's really the key for these things we say, and the things can refer to embedded systems, but then when they become connected, they become in Internet of Things. The reason we have to define them as Internet of Things that they might have some unique characteristics that are somehow different than the cyber physical systems and the embedded systems. But there are strong relationships across all these three systems, and the challenges are sometimes are the same. So the way I would summarize them is IoTs have embedded systems, I mean cyber physical systems, but not all embedded systems and cyber physical systems are IoT systems. So you can't just say any typical embedded system is an IoT system. You can't say that. You can't also say that any typical CPS is an IoT system. You have to have those infrastructure to call it as an IoT, because when you define as an IoT, you relax some of the constraints that does exist in embedded and CPS. So the constants that I'm going to talk about have more stringent requirements for CPS than IoT. IoT has less sort of stringent requirement than CPS. Now let's talk about the architecture of IoT. Obviously, we think about running the different applications, IoT applications, as you see here. Then we have these IoT gateways. These gateways are going to be obviously used to take the information via the sensors and some other sort of infrastructure elements like cameras, lidars, radars, different sort of equipment you can use to get the information and then pass it to the embedded system for processing. So you have the different sort of processing elements at the end to process those information. In terms of the infrastructure, if you divide it into the different components, you will see that it does have a sensing part, it does have a transmission part, it does have a processing part, and then obviously you have to enable different technologies to support these different components in the infrastructure. There are some major tasks in IoT. For example, you need to tackle the core technologies. You need to speed up the standardization. There are many standardizations still left to do because there are standardization needs to happen across different domains and so on. Coordinating industrial development, developing applications, regional planning, and then the information security and public services. Then the requirements for IoT systems are going to have, obviously, they should have some communication capability. They should have the memory to store information. They have autonomous and proactive behavior, context awareness, and collaborative communications. Now, in today's talk, I'm going to talk about two major constraints in cyber physical systems or IoT systems. The reason why I say both cyber physical system and IoT is because these constraints do exist in both systems. It might be a bit, the specification of this constraint might be a bit different in either of these systems, but they do both exist in there. In terms of constraint, some people ask me, well, what is a constraint? A constraint is kind of a sort of behavior, I would say, that needs to be achieved by a certain system to operate it successfully, right? So a performance constraint is going to indicate that you need to have a certain level of performance to operate a cyber physical system or an IoT system. Same for the security. You need to have certain security mechanisms in place to protect from vulnerabilities in cyber physical systems or IoT systems. The challenges, I mean, why there are challenges in these two sectors? The reason is, we have to keep one thing in mind, that these systems are not heavy systems. So they're very lightweight. You cannot use any expensive protocol or algorithm in these systems. So they have to be very, very lightweight and need to execute very fast and efficiently. Performance indicates that we need to perform quicker, so we need to accelerate the processing, we need to allocate the resources efficiently, and also we need faster feedback in terms of control loops and so on. We need to get the feedback very quick. That's kind of the thing that we need to focus on in terms of accelerating performance. So for example, I mean, a certain cyber physical system or an IoT currently process some data maybe within in 30 minutes, and you see that without compromising any sort of accuracy and any sort of output behavior, you can reduce it to 15 minutes. So that's definitely a performance improvement, and everyone is gonna like it. So, and we always have that target. That's going to drastically reduce the cost of operating the system. The other one is the security. That's becoming an increasing concern in IoT systems, primarily because it's exposed to internet. And as you know, that internet has lots of vulnerabilities in there. And when you go into this hardware level, this becomes even more sophisticated. The reason is, these attacks can cause a lot of effects to the end users. So definitely you need to figure out the impacts and risk and some sort of resolutions for those attacks. Now I'm going to talk about some performance improvement considerations in this sector. So first of all, one technology that has come along in this area, either in the CPS or IoT, is the edge computing. And this has become a very hot topic recently, and it's gonna become a hot topic for some time. The reason is what we have realized, that applications that we run on these systems are now demanding more than what they used to demand. So we need to find a way, how can we run this added workload or added computation in an efficient way. So edge computing is considered as a cost-effective and predictable way of executing this added workload. But we have to have some considerations. I'll discuss it in a moment, but mainly it's just saying that we have some network nodes, and there are two things in there going on. One is the edge and the other one is fog. Sometimes these two terminologies are being used alternatively, edge and fog, but there is a difference between these two. When we say edge, then it's usually connected by wire, and when it's fog, then it's wireless connectivity. But in both cases, proximity is a factor. So the node that's connected to, it needs to be within the proximity of the system that we are connecting to. So that's really the key factor here, so that we don't really go to a remote server to compute something and then the latency becomes really unpredictable. So the main goal of using edge computing is going to be definitely a predictable latency and computation. In the machine learning world, we know that this has become a kind of a de facto standard now for many of the work we do today. So many of these embedded systems now require, or cyber physical systems or Internet of Things, they require to be smart. And to enable this smartness, you need to add machine learning. But machine learning algorithms are heavy. Usually, we'll talk about it. But the thing is, we need machine learning. There is no way to escape around it. The question is, how do we effectively run these ML algorithms in this infrastructure? And how do we get some sort of performance improvements? So that's what I'm going to talk in the next few slides. So here we are seeing that we have some cloud server, we have some edge devices, we have some end devices. And then definitely what's happening is when we have these neural network functions that we need to execute today, if you think about it, on these IoT systems, they usually offload that ML part or the neural network part to a remote server, to a cloud server. So they connect it to the cloud and they compute it on the cloud, and then they send the data back to these IoT systems, because these IoT systems are incapable of running those models. Now, the problem in doing it is obviously you are making this whole data, communication part unsecured, because there might be an attack that can happen when these IoT systems transport over the data to the cloud. So that's one vulnerability. There are other issues like latency. The network latency can be very high. So for example, you need to compute very simple thing, and then if you need to send that data down to a remote location, then definitely that's not gonna be well ordered if you consider the network latency part. So we need to definitely do something, right? So rather than blindly offloading all the ML part to the remote servers, we need to think about some smart ways of handling these ML jobs or ML tasks. So this is what I was just saying, that we need to find some solutions so that we can also rely on the IoT systems or embedded systems to kind of utilize its resources, not just offload blindly to the cloud computers. So one way we have done it in our lab is by doing the input splitting. What does it mean? Is you have certain workload, you have certain ML tasks that can come on the IoT nodes or the embedded nodes. And in there, we first calculate those tasks post-execution time. So we first calculate the worst case execution time of those tasks, and then we perform a schedulability test on that node to check whether they can run efficiently on the embedded node. Because if they can run on the embedded node, then we don't really need to offload that to the cloud blindly, because that can be sufficient enough, because you don't want the embedded processors to be unutilized. So we first check that. And if we see that the embedded systems are incapable of doing it, then only we send the data, remaining data, to the edge node or fog node. So rather than sending all of it to the edge node, or rather than keeping all of it on the embedded, based on the need, we split it into two. We keep as much as we can keep on embedded, where there is no network latency because it's running locally, and the remaining is going to the edge node and then get the computation done. So this is we call input splitting, and we have a publication on it. So this is just a diagram how we do it. So we have developed a delegator on an embedded device. So we use Raspberry Pi to do this experiment. And then we have the data streams coming in, and then we use the delegator to kind of do that decision making, whether we want to keep it or we want to send it off to a fog node. Then the second way we also do is we look into the neural network layers. We dig down into the neural network layers to see how this is operating. And when we dig down into these neural network layers, we figure out that there are different layers and then they operate in a certain way. And we can potentially break the neural network layers. And the way we can break it, the yellow boxes you see, in those places, we actually can break the neural network models, and we can partially get the results. The reason we think that this is gonna be a game-changing situation, because not in all applications we need the 100% accuracy, or we don't need 99% accuracy. In some applications, as long as I have a certain accuracy, I should be good. Maybe 90% or maybe 80% is good enough. I really do not need the highest accuracy, but I do care about the timing. I want to execute the model faster and get a decision rather than waiting too long to kind of get a decision. So that's why this neural network splitting is a very interesting mechanism for us to kind of also see how we can offload the computation to the fog node or edge node. So in this case, we run the partial model on the embedded device as much as it can run, rather than, because we know that the full model might not be able to run on an embedded device. So we run a partial model, and then we run the remaining one on the edge node, and then we basically coordinate the results and make it appropriate for the application. So that's really the other way of doing it. So we built these neural network models. So these are some of the implementation details. So we use TensorFlow, and in the TensorFlow, we have this TensorFlow for the IoT device. And we also have the TensorFlow for the edge node. And then we build these neural network net for individual places. And then we do have some delegators and so on. One other thing that we do as well is we calculate the entropy. So the entropy is really indicating the efficiency of the ML model, whether we are happy with it or not. Because if the entropy value is in a certain threshold, then basically we stop it, and we don't really need to continue these neural network calculation anymore. We can just publish the results. But if the entropy value is not meeting the threshold, then we still continue with the technology that we are saying that we offload based on whatever is required. In the experiments, we use three different models, model 0, model 2, and model 3, three different neural network layers based on the applications, because different applications demand different neural networks to be designed, from simple to complex. So we use three different data sets. We use a wall turn data set, which is a robotic data set. It's a textual type of data set, sensor-based, where we have the wall turn different data sets. These are pretty simple data sets. MNIST data sets and the Cipher data sets, which are more image-driven and then heavier data sets. So we don't really need to use the convolutional layer for the model number 0, which is very simple. Model 0 and model 1, we don't really need the convolutional layers, but for model 2 and 3, we need convolutional layers because we have these complex data set that we need to process and train, so we need to use those. So we compare it across three different thing. Obviously, the status quo research is the one that just offloads completely, either keep it or offloading it completely. But in our case, we have two proposals. We do input splitting, where we look at the values of the worst case execution time. So we divide it based on the time requirement, and then we process it that way. So that's one. The other approach is splitting the neural network layers. So the second two, these two are our own. And we also do some sort of analysis on the network latency, how much time it takes. So as you see, model 0 is very simple. Model 0 takes a very small amount of time to execute on the embedded node. And if we look into the overhead, then in there we see that obviously the fog node takes less time because it has higher computational power than the IoT node. So it's quite acceptable, these numbers. But the problem is this latency, right? So if you add this latency with this red number, then you will see that this value is even more than the blue. So actually, we don't really need to offload model 0 to a fog node. We can keep the model 0 on the fog node, on the embedded node or IoT node and execute them locally rather than offloading them. So this kind of values are telling us that there is an importance to have an offloading mechanism. So you really do not need to offload the complete model to an edge node blindly, or you don't really need to keep it locally, even though it may not be able to run it properly. So rather than doing it, you basically decide at runtime what you should do based on the need and the latency and so on. So that's what we do. Similar thing happens for model 1. We see that model 1 also doesn't need that much to be offloaded to the edge node or fog node. I mean, it partially, you can send it off. Model 2 is actually good to have offloaded partially. So because you can actually keep up to the point where your embedded node is going to be able to execute most of the task, and then you offload the remaining. But model 3 definitely requires some sort of offload because they cannot be run on an embedded node or IoT node. So you can keep certain portions on embedded, and then you just execute the remaining portion to the edge node and then do back and forth. But one thing though, if you want your accuracy to be not that great, you potentially be able to run everything on the embedded node. But so you can play with the accuracy values and the entropy values and the dropout values. But what we are trying to show here is, you can actually improve the performance of a system by changing the requirements. So if your requirements do change, you can potentially make that change without even doing any sort of fundamental changes in the design, because this is more dynamic. We also try to mix it up. I mean, rather just to make sure that we are doing something. So we have embedded system offloading, then efficient offloading, all these things. We also do the model splitting mixed as well, and to see how they work. And we got a very good result because the accuracy and everything is as per to the local one. Any questions for this performance part? If not, then I'll continue. So now the performance part. Oh, yeah, I see a question. Yeah, raise the hand. Go ahead. You're on mute. If you're on mute, then I probably can hear you.
Can you hear me now?
Yeah, I can hear you.
Yeah, thank you for your talk. I mean, I have now, based on what you will decide that this part will be on the IoT device and the other will be on the fog or on the edge. It's one process.
Yeah, so we are going to decide. So we have a delegator, right? We have a delegator implemented. So in the delegator, we are going to we can look into two components. First, if it's a input-based splitting, we look into the timing, how much time it takes to execute. And then based on that, we decide how much we want to keep on the embedded and how much we want to offload. If we want to go for the neural network splitting, then what we can do is we can look into the end. So we run the partial model, we get a certain number of accuracy, and if we are not happy with that accuracy, then we go into the fog node and then do more of run on the fog node or edge.
So you will continue learning there, or like you continue experimenting, or you start from scratch?
No, we'll continue experimenting. So the results are saved and synced. That's the beauty of it. We are not starting from scratch. Yeah.
Okay.
So they're all synced up. So these edge and embedded, they are both synced. And because we wanted to do that sync, we cannot break it everywhere. As you see, even though we have these models, we can break the model at just the yellow part. Because if we do the break and other part, then the synchronization will be lost, and then we will not have the convergence.
Yeah, exactly. Thank you. Yeah, clear. Thank you very much.
Perfect. Okay, so now the security considerations. So this is the other thing that we have been looking as well in the IoT worlds, and security has become a very, very big field, as you all know. And one of the attack that we have started looking into this IoT software system is the fault injection attacks. The fault injection attacks are actually injecting some sort of faults into the system to check, how your software is doing and whether it's robust enough, and then what happens and so on. So the fault injection attacks can happen using different ways. It can happen through clock glitches, jump faults, unauthorized system access, data theft, voltage glitches, electromagnetic glitches, and so on. And it happened in the past. If you look at the literature, you will see that there were fault injection attacks on the CPU, and they have shown how they have done it through the flash memory. And also it happened into the machine, the ATM or like the slot machines, where the electromagnetic interferences cause some glitches, and then that caused the attacks to happen. And obviously these attacks are not acceptable, because they cause a lot of financial loss, reputational loss, and unavailability of the system. So this is just obviously a challenge that if we have some sort of instruction level fault injection, then can we use any pattern checking or history based information to see whether there is potentially an attack in the system? Because if this hasn't happened in the past and suddenly it's happening, so something is wrong. So you can potentially use that pattern matching, which is potentially the machine learning side of it, to check whether there is any attack happened. And this is basically just explaining how such low-level attacks can happen. Instructions can be skipped because of clock glitches, and these clock glitches obviously are happening by an attacker, and then also an electromagnetic attack, how that can cause the changes in the signal, and then that causes the system to behave strangely. So the goal here is we need to use some sort of historical information to see how we can potentially detect that attack. The problem we found in there is not a data set available for it, because if we need to do that kind of history-based checking, we need to create a data set that can potentially be used to detect any faults after. The other thing that we have found is there are no application level information being used, because sometimes what happens if we plug those values with some generated values, then we kind of know, okay, what application values may cause a potential impact to those low-level attacks and so on. So so that's why, you know, we look into it, and then we look into the background and so on, and we kind of try to go into the bit level first, and to create a fault injection attack data set, and then we later on plug the application with it, and then create a supervised learning data set to figure out any attacks that can happen at runtime. So this is just another example how you know, you can have an attacker attack the system. So if you have a jump instruction attack, then if there is an if block which should not be executed, it's going to be executed because of the jump instruction attack, and that can cause your system to be authenticated and then do some sort of bad actions to it. Now, the tool that we used to create that data set is the Chow's duck fault injection tool that can help you to work on an executable. So you basically use an executable, and then you use this tool. It extracts the assembly instructions from the executable, and then it just you know, creates some faults in there. So this tool is readily available in the web. You can just download and use it. So we used it. This is not our tool. This is an open source community tool that we use to inject some low-level fault injections. And then we run the executables, and then we also record some execution output, because we want to create a supervised data set, as I was telling, because we want to know, okay, which application values are going to be affected by these changes, because not all, as you see, because this if block is not going to run for certain things. So obviously we need to know which application inputs are going to be affected. So we first want to build out a general ML approach that can be used to detect fault injection attacks. And then we also want to see how these application input values are, have some sort of impacts with these detected threats. Whether, you know, if we have some application values that we plug in, maybe the detection accuracy will increase. We'll see that in the results, whether that helps or not. So the way we, again, do it, we first use the Chow's duck software fault injection. We feed some executables, and then we get some data out of it. And then those data or logs are being fed into an unsupervised learning, because at that time we don't have any levels. So we use unsupervised learning. We use some clustering methods to create a model. And then after that, we use that model and the logs, and then also the application input to create a supervised learning that becomes the model number 2, because we just want to compare the model number 2 and the model number 1 and see, you know, whether the application has any impact on increasing the performance of the detection approach. So that's really the thing is happening in here. So we have two models. We first use the unsupervised learning, and then we kind of use that model to create another model by just padding the application input in here. So this is just the stage 1, as I was saying, and the stage 2, obviously, this is the thing. And this is how we are kind of doing the comparison. So we are comparing the outputs of model 1 and 2. And then if the model 1 and 2, they are both saying that, okay, you know, they're saying, they're basically not saying anything different, then there is no threat, right? And so if they are saying not different, not the same, so then there is a potential threat in there, which might be true, which might not be true, because there will be some false positives and false negatives. But that's what we do care more, because if we see some sort of differentiations in terms of the results. The case study that we worked on is a smart home system, Nova Smart Home. So in the Nova Smart Home, it's also an open source available online. So what we did is we used that and then we varied the temperature, we varied the light intensity, and then we got some output logs for sure. And then also we use this Chow's duck tools, fault injection tool to inject some low-level faults. I mean the assembly type of faults in the low level and create some levels. So out of these, we created almost more than 400,000 instances of the non-instruction fault, the flip, and the no operation. So these are the fault models that we have. So we have some changes on these. Obviously, we did make those altering to create the data set. And when we create the data set, after that, we use the model 1, as I was saying, and the cluster was 4, and then model 2 was trained as well. And we obviously compared the results. And then we got some, lists of values. So we have some output logs, and we have some predicted threat and the actual threat as well. So there are some false positives, there are some false negatives, as I was saying. So the next slide is going to show the accuracy. So for the no operation NOP fault model, the recall value was around 85%. The recall is important for us. That's the most important metric for us, because it tells you, how bad is your machine learning model in terms of predicting the fault. So the higher value, obviously, the better. And we are getting around 85%, which is not a bad number. So high F1 score is gonna minimize the both incorrect and the correct one. But for us, the recall is the most important metric that we can think of. We did another comparison, as I was saying, with the application data. So with the application data in place, when we have a range of application data, we varied. For example, if you have a temperature varying from -30 to +30 versus -5 to +5, and when we use that information in the supervised learning and plug it in, so we basically get higher recall value compared to providing some small ranges of values. So when we provide small ranges, our recall value goes down. So that definitely makes sense, because the higher ranges you cover is basically covering more attack surfaces and more samples, and the training becomes more robust. So that's all for the fault injection side. Now, this is one approach how we can secure an IoT system. We definitely have some methods in place. This is just one of the methods that I discussed. There are other things that we have done as well. But it's just saying that, we can incorporate some fault detection methods or fault prediction methods, or even anomaly detection methods at runtime to increase the security or to make the system more secure. So that's one approach that we can take today. So you probably have a system running. You don't want to change the design of the system. You want to keep the system running. So you want to just add some methods or algorithms in there to make the system less vulnerable, to make it more secure to operate. The other approach that we can take today as well is a secure by design, which means that when you design the system, you make it such a way that certain attacks are never possible. Even they are possible, they don't propagate to the different components. So if your one component is affected, then it's not going to affect the other. A typical example could be a kernel, right? So there are two popular architecture in the whole world. One is called the monolithic architecture, and the other one is the microkernel architecture. The Linux is a monolithic architecture, and QNX is a microkernel architecture. The problem with the monolithic architecture is everything is under one process. So in Linux, if you have certain processes are affected by some security vulnerabilities, it can crash the whole kernel because there are a lot of dependencies in there. And if your root process is affected, then it's going to crash the whole system. On the other hand, in QNX, you have a microkernel architecture. So every utility is a process. Every activity is a process. So if your one process is killed, you are still fine because your other process is going to still run. So QNX is very, very robust in terms of providing reliability and efficiency, and that's why it's been used in many of the cars, including Tesla, especially in the instrument cluster side, where we need the reliability and efficiency and so on. So secure by design is very, very, very important, and we should definitely consider this when we design the next generation system. Now, with respect to that, I would like to talk about something different, which is called containers. So containers are very popular in the cloud world today because they provide an isolation at the operating system level. It provides a certain level of virtualization. And it's ideally immutable because you cannot change it. Once you have something enclosed inside a container, you potentially cannot change it. So obviously it's providing a greater level of isolation. And isolation is a key aspect in the secure by design. You want to isolate as much as you can. You want to make things independent. Less dependency is better because that way one component is not going to affect the other component. So there are two types of containers in the space. One is called the operating system container. The other one is the application level container. So in the case of embedded systems, we have Docker Compose, which is the application level container. And on the operating system, we have different containers for different operating systems as well. So the way you differentiate, as you see, for the if you have a very crude level of virtualization, actually they belong to different sort of virtualization. So you have a container runtime, and then you run the different apps on the container runtime. And in the other case, you have a kernel sitting, and the kernel is having a container, and then you have the different apps running. So even if you do not want to use an operating system, you still can have the containers, but those are more into the virtualization world. But again, this is under the host kernel, and then you have this is under a virtual machine kernel. Now, the containers are not that difficult to deploy, and then it's providing an isolation as well. And then you can definitely add some security features as well to just make sure that you have the proper authentication to connect from one container to the other container, and you can have all of these properly maintained. So one concern about using container is the performance. So what we did is we did create a test bed in our lab to measure the performance of different containers that we can deploy on IoT systems. So we use obviously the Raspberry Pi, and then we use the different operating systems, and we just use the different containerization to enclose it and see how they work. And we found that there is minimal performance issue in there. So this is the test bed that we did work on. So we use the Raspberry Pi 3 Plus, and we have some Arduino Uno board and some breadboard with some sensors, and we have some routers, and we also ran some Kubernetes cluster, which is used for orchestrating the workload across the different sort of agents. And this is a kind of the detailed design. How did we collect all the data and so on? So we have some MQTT broker to send the data off from the server to the client. So we had some MQTT clients on the Arduino side, and then they were just continuously communicating with some information that we need to check and see how much overhead it's adding. And we tried with different threads as well, but we didn't see much overhead. So the overhead was minimal compared to the benefits that we can get. So definitely this tells us that we can deploy containers in the IoT world. It does not require to stay only in the cloud world. We can also do it on the IoT side of it. Now, how they can be beneficial for next generation vehicles. For example, you have different functions in the cars. This is just a use case explaining how containers can be beneficial in the automotive space. We have the infotainment unit, we have the telemetry, we have the instrument cluster, and so on. And there was an incident happened in the 2015 where the Jeep Cherokee vehicle was attacked remotely. And later on, they figured out that they got an access through the telemetry system that we have even today in the car. So the attackers can try to potentially log in through some sort of external interfaces, and if they can some way get an access to the CAN bus, then they can attack the system. If you have containers, they are going to be practically quite impossible to do, because you have a greater level of isolation. If one component is compromised, then it's not going to compromise the other sections. So there are lots of benefits to this kind of architecture. And so we have an architecture proposed where we have the different containers to enclose the different activities of the system. So it does not need to remain only in the automotive space. Any IoT applications can utilize this kind of architecture, where we have a secure by design architecture proposed here. In addition to that, we also explored some languages that we can implement on this space. So we might still think, oh, even though we have containers, we have isolation, the attacks can still happen. And how do we even check at runtime that there is no security violation? So there is a mechanism to do that as well. This is called RASP, Runtime Application Self-Protection. In RASP, you can derive some policies. So this is just a concept. So we have a paper on it as well. And in this concept, you can use certain languages to implement in this kind of system to check certain properties at runtime to figure out whether there is any violation of any security policies. So you define some security policies, and if these policies are violating at runtime, you kind of go into generating an alarm, or you might go into a safe mode or something. And if you have isolation on top, then that's fantastic, because then you can just eventually you are safe, because it's going to affect only a certain container, not really the other containers, because they are completely isolated. So this is just an added protection, and we can also implement the RASP, and this is kind of an architecture how we can implement the RASP monitor on such a container environment. So we can get certain information from the containers, and then we check certain properties, and via that we can also ensure the security at runtime. So this is just another architecture for connected vehicles, how we can do that for vehicles. So in summary, we discussed today 3 things. First, the performance, where we saw that the performance improvements can happen by splitting the task into the embedded and the edge node. So we looked into the ML task, but it can potentially be done for any task, irrespective of ML, non-ML, and so on. You can do it in 2 ways. Either you can split the models that you are running, or you can split the input. So if you can some way find out the timing requirement of the task, and then you can break down the task, and then you can partially run certain task on the embedded and the remaining to the edge, and then the overall performance is going to be much better. The other one was on the attacks, where we saw that you can have some attack detection at the lower level, where you can utilize some sort of machine learning models to see what happened historically, and based on that information, you can detect some attacks. And the final one was kind of the design driven. So you can make a secure by design system where you have a greater level of isolation, so that your attack surfaces become less, and then you are protected. And on top of that, if you add some security policies, you are going to be even more protected. So that's all for today.
Okay, thank you so much, Dr. Akramul, and really insightful talk. I would like to leave the floor open for any questions from the audience. If you have any questions, please raise your hand. Otherwise, type your question in the Q&A box, and I'll try to convey that. But meanwhile, I do have one question. So in the first and second part, you were talking about the performance and security, and often they have contradictory goals, right? So in a sense that the best performance or a system with the best performance usually does not have this overhead of security, and a secure system might have kind of overhead, and that hurdle the performance, right?
Mhm.
Maybe can you elaborate on, for example, in security by design, how to have this kind of trade-off between security and performance, and how can we ensure maybe a good enough performance while satisfying the secure by design requirement?
So that's a very, very good question. So I always tell that to my students, the safest car in the world is the car that does not drive, because you don't need to drive that car. So that's the safest car. So, we always have to balance out the constraints, and that's why I name it as constraints, because the performance constraint has some negative impacts on the security. If we focus on performance too much, we might compromise security, and vice versa. If we focus on security too much, then we are gonna compromise the performance. So balancing them is gonna be the way to go. But the way I see it, it's gonna happen by designing a multi-mode system. By multi-mode, I see that, if I need to operate, rather than redesigning it again and again, I design it from the beginning in such a way that I might have a different operational mode of my system. So I might have a performance mode where I go for acceleration, and I might have a security mode where I go into the full secure blown mode, and I might have a mixed, which I have some balance out of performance and security. And if I need to, and it also depends on, different threshold values, what I want to achieve, how much performance I can compromise, and so on. So we can potentially develop a tree structure type of design where we can actually surface into different decisions based on the requirements of the system at runtime. So what I have seen so far, that if we know all the different ways the system can run from the beginning, then and design it in such a way, then the system is going to be more predictable and efficient. But if we don't know, then it's not going to be that efficient, but still possible, because people want not to redesign the system and again just because a different requirement comes in. So I would say that, the secure by design or performance by design, all these systems are going to be the great systems if we do not consider them only individually, but also together. So by doing such a multi-mode system, we can potentially enable that.
Okay, that's clear. That's actually a good way to balance security and performance.
Yeah.
Okay. Any again, one more round. Do you have any questions from the audience? If not, I think once again I will thank you, Dr. Akramul Azim, for this nice seminar. And again, I'll just remind the audience that we will have probably a seminar, a third seminar by Dr. Akramul Azim next Monday. That will be in person in KFPM. So I hope that to see you all in the next seminar. Thank you, Dr. Akramul Azim, and
Thank you.
have a good night.
You too. Thanks. Bye. Thanks everyone for attending.
Thank you. Sorry.